Good day, my wonderful students. I welcome you all to this segment of learning. I am your physics teacher, Mr. Emode Kingsley. Today, we are going to be learning the topic wave-particle duality. Just as the name implies, wave-particle duality. The word duality simply means having two different descriptions. In Ss2, we have already studied wave, and we define wave as a disturbance that travels through a medium, transferring energy from one form to another without causing any permanent displacement of the medium. Then the other one, particle. A particle is a small localized object or entity which can be ascribed several physical or chemical properties such as mass, density, and volume. But in a broader sense, particles are physical things that we can count. Matter in form of light or electron exhibit two properties. That is, it exhibits the wave property and also particle property, but cannot exhibit both at the same time. Hence, we have two different theories of matter: the wave theory and the particle theory. One can simply define this wave-particle duality as the phenomenon of matter in form of light or electron to behave as wave or particle, but not simultaneously. At the end of this lesson, all the students should be able to, number one, just like I said, at the end of this lesson, students should be able to, number one, identify phenomena which are only satisfactorily explained by assuming that matter behaves like A, waves, and B, particles. Number two, explain the uncertainty principle and give examples. Now, let's look at the phenomena that we can rightly explain by assuming that matter behaves like wave. Number one, the phenomena that can rightly be explained by assuming that matter in form of light or electron behaves like wave include I, electron diffraction or the diffraction of light; II, reflection; III, refraction; IV, interference; V, polarization of light; VI, wavelength or frequency. Now, let's look at the phenomena that we can rightly explain by assuming that matter behaves like particle. Now, the phenomena that we can rightly explain by assuming that matter behaves like particle include I, emission and absorption of light; II, the photoelectric effect; III, thermionic emission; IV, Compton effect; and V, radiation from heated bodies. This is also called the black body radiation. This wave-particle duality was suggested in 1924 by a man called Louis de Broglie. De Broglie postulated that any particle with momentum has an associated wavelength, and this wavelength is now called de Broglie's wavelength. And mathematically, it is given by mathematically, this de Broglie's wavelength is given by delta dB is equals to h all over p, where h is the Planck's constant. And p is the momentum of the particle. Since momentum is mathematically expressed as P is equal to mv, this de Broglie's wavelength can also be written as lambda dB is equal to h all over mv. We are now going to take some calculations to determine this wavelength. We take the first example. Now, looking at the example on the board, what is the speed of an electron having wavelength of 1 times 10 raised to the power minus 7 meters? And in bracket, we have the Planck's constant to be equal to 6.6 times 10 raised to the power minus 34 joules second. And the mass of the electron equals to 9.1 times 10 raised to the power minus 31 kg. That is kilogram. Now, let's look at the solution. Before we can solve effectively, let's write out our parameters or the quantities given. The first parameter given here is the unknown, which is the speed. And speed is represented by the letter V. So we have that V is the unknown. Now the next parameter is the wavelength. Writing another parameter, we have that the wavelength is equal to 1 times 10 raised to the power minus 7 meter. Then we have other parameters in bracket. Now, let's bring out our formula for the solution to this equation, which is the de Broglie wavelength equation. Using that equation, we have that lambda is equals to h all over mv. And because we are looking for v, if we make v the subject formula, we'll be having that v is now equals to h all over lambda m. Now let's substitute. If we substitute, we will now be having that lambda is equals to, that the velocity or the speed of the electron is equal to 6.6 times 10 raised to the power minus 34 all over the wavelength is 1 times 10 raised to the power minus 7 multiplied by the mass of the electron, which is 9.1 times 10 raised to the power minus 31. If we calculate this, we will have the final answer to this question, which is 7.3 times 10 raised to the power 3 in meters per second. Take this next question as an assignment, and this assignment you will solve it, submit to your parents to mark. In the next class, we will look at it and solve together, and I will provide the answer. Now let's look at the assignment. A particle of wavelength 6.0 times 10 raised to the power minus 7 meter behaves like a particle of a certain mass. What is the value of the mass? Then in bracket we have the Planck's constant as 6.6 times 10 raised to the power minus 34 joules second. And C is the same thing as the speed of light, which is 3 times 10 raised to the power 8 meters per second. So you do that at home and submit to your parents. In next class, we will solve it together and get the answer. Now, let us look at the second objective, which is the uncertainty principle. Uncertainty principle. Heisenberg, a German physicist, came out with this uncertainty principle, and he states that it is impossible to know accurately the exact position and momentum of a particle simultaneously. Or in other words, there is always an uncertainty in determining the position and the momentum of a particle at the same time. The uncertainty in the position multiplied by the uncertainty in the momentum approximately equals the Planck's constant. And mathematically we can write this as delta x multiplied by the delta p approximately equals the Planck's constant, where delta x is the uncertainty in the position, delta p is the uncertainty in the momentum. Then we also have other complementary variables, just like energy and time are complementary, meaning that you cannot determine the energy of a particle and the time of determination at the same time. So we can also write that delta E multiplied by delta T approximately also equals the Planck's constant. And finally, the other complementary variable is position and velocity. You cannot get the position of a particle and its velocity at the same time. Hence, we have that delta x multiplied by delta v approximately equals the Planck's constant. Let's pick some calculations on this. We take the first example. Okay, now let's look at the example. An atom radiates for 1 multiplied by 10 raised to power minus 7 seconds to emit a photon. Calculate the uncertainty in the energy of the photon. And in bracket we have the Planck's constant as 6.6 times 10 raised to power minus 34 joules second. Let's look at the solution to this question. But before we solve, we have to write out our parameters to solve effectively. The first parameter there is uncertainty in time, which will be given by 1 times 10 raised to power minus 7 seconds. Then we have to calculate for the uncertainty in energy, so we are looking for delta E, and that is unknown, where the Planck's constant is 6.6 times 10 raised to power minus 34 joules second. Now, let's bring out our equation for the solution to this question. If we look at the three uncertainty equation here, the one that corresponds more is the second one. So we have that delta E multiplied by delta T approximately equals the Planck's constant. Now, if we make delta E the subject formula, we will be having that delta E is equals to h all over 2 pi delta T. Now let's substitute. If we substitute, we'll be having that 6.6 times 10 raised to power minus 34 divided by 2, knowing that the value of pi is 3.14, we use 3.14 multiplied by the uncertainty in time, which is 1 times 10 raised to power minus 7. If we do the summation and find the final answer with our punch card, we will have that the final answer is 1.05 multiplied by 10 raised to power minus 27 joules. So that's the final answer to the question. Now, the next question, we are going to take it as an assignment, which you also solve and submit accordingly to your parents. Okay, the assignment goes this way. The question number 1, if the uncertainty in the momentum of an electron is 1 times 10 raised to the power minus 22 kilogram meter per second. Determine the uncertainty in its position. And in bracket, we have our Planck's constant to be equal to 6.6 times 10 raised to the power minus 34 joules second. Question number 2. Explain what is meant by the duality of matter, illustrating your answer with observable phenomena. This assignment should be done and submitted to your parents. In our next class, we'll look at the answer to this question. In conclusion to what we have done, we have been able to look at the wave-particle duality, the observable phenomena that you can use to explain that matter behaves like wave and also behaves like particle. And we have also looked at the Heisenberg uncertainty principle. We'll be expecting to meet in our next class. Stay safe at home and avoid every avoidable. Thank you very much.